Okay, so picking up with part 2 of the Applied Functional Analysis Practice Final Exam, here's number 4. Consider the nonlinear integral equation given here for this u of x. Okay, equals that sine of x plus lambda integrated integral 0 to 1 k xy hyperbolic tan of u of y dy, where our absolute value k of x comma y is less than or equal to m. Let x equal c 0, 1. Okay, so for here, a, b, c, d, e, f, we want to define this operator for f corresponding to the equation. Show that f maps x onto itself. Show that this norm f of u minus f of v infinity is less than or equal to this on this side. Some of this stuff I'm not going to say because the symbols are there. It just adds a lot of words. Part D, determine a condition on lambda ensuring f is a contraction. Part E, use Banach's fixed point theorem to establish existence and uniqueness. Part F, describe the corresponding Picard iteration. So this is a contraction mapping theorem problem. So for part A, we define the operator given u of x above. So we define that f. Okay, for that C, 0, 1. Let's go to Z, 0, 1 by this fu x equals sine x plus that lambda integrated of 0 to 1 k xy hyperbolic tan of u of y dy. And a fixed point of u equals that f u solves the integral equation. For part B, we're looking for this mapping here. F maps x into itself, assuming k is continuous in x and y, and u is an element, and that's C, 0, 1. Then hyperbolic tan of u of y is continuous and bounded, and we get this integral here for that x mapping onto the 0 to 1 k of xy hyperbolic tan of u of y dy, and that's continuous in x. And since sine x is continuous, that f u, that's an element in that C of 0 to 1. And pardon me if I kind of, I don't know if I'm not using formal mathematical terminology for some of this just to save some time. But the symbology is correct. Okay, let's move along to C, D, E, and F on the second page here. So, okay, so C, D, E, and F. Okay, so this is interesting for letter C. We want to show that following here, the letter C, remember we wanted to show this. Okay, so we're going to use that Lipschitz estimate, and for UV in element X, we're going to get this whole thing here on the left. Okay, the FUX minus FVX equals this lambda times this integral from 0 to 1, this k of xy times the quantity hyperbolic tan of u of y minus hyperbolic tan v of y dy. So single variable integration there. Well, for this, just dy rather. So taking absolute value of this on the left-hand side, and on the right-hand side, now we have the absolute value of this whole thing. And since the absolute value of a tan, hyperbolic tan A minus hyperbolic tan B is less than or equal to A minus B, and that absolute value of K xy is less than or equal to M, we could say the following: this absolute value of the difference here between the f u x, f v of x, less than or equal to absolute value of lambda m integrated from 0 to 1 of absolute value of the difference between u of y and v of y dy. And since the absolute value here of the difference between u of y and v of y is less than or equal to the norm of a difference between u and v infinity, we get this norm here, infinity, f u minus fv, less than or equal to absolute value lambda, that absolute value m, norm infinity u minus v, or norm, some people would say u minus v infinity. I've heard it numerous times said both ways. Taking the supremum over x, we get this norm here, f u minus fv infinity less or equal to absolute value of lambda, and then m norm u minus v infinity. Okay, and that's technically just an m. I'm sorry if I said m was taken an absolute value of, so here there was no absolute value sign there. Let's see. So moving forward, contraction condition. I apologize if any of this, any steps weren't more explicitly defined here. I know this. Some of the stuff is just more in detail. Some of it should have had more detail. Part D, contraction condition. F is a contraction if absolute value of lambda m is less than 1. And thus, absolute value of lambda is less than 1 over m. And that's if, condition that we have to say, if m is greater than 0. Letter E, existence and uniqueness. Since C of 0, 1, with the following is a Banach space and F is a contraction, when we have this inequality, Banach's fixed point theorem implies that F has a unique fixed point. Therefore, the integral equation has a unique continuous solution. And for the Picard iteration, choose any u0 as an element in C of 0, 1, and define u sub n plus 1 equal to f u sub n, and explicitly u sub n plus 1 x equals that, now the sine x plus lambda times this integral from 0 to 1 k of xy hyperbolic tan of u sub n of y dy. And then we could say u sub n going to u and uniformly, where u is the unique solution. Okay, so that's number 4. Moving along now to number 5. Okay, so for number 5, we let x equal that, we have that L2, 0, 1, consider e sub n of x equals square root of 2 sine of n pi x. Show that e sub n is orthonormal for A. For B, show that norm e sub n L2 equals 1. Show that e sub n 0 weakly in L2. Show that e sub n does not converge strongly to 0. Explain the significance of weak convergence for existence proofs of PDE solutions. So this is a Banach spaces and weak convergence problem. For the orthonormality, we're going to let e sub n equal this, okay? And we're going to compute the inner product here, e sub n, e sub m. It's going to give you this integral from 0 to 1, 2 sine n pi x m pi x dx. And using the standard sign orthogonality relation, this integral is 0 to 1 sine n pi x sine m pi x dx equals this piecewise. We have 0, comma, where n does not equal m. and 1/2 where n equals m. So that inner product there, that equals that piecewise that we're given here, that we were given here rather. And so E sub n is orthonormal. Okay, for part B, a norm from orthonormality, the norm of this E sub n, that L2 squared, that equals the inner product of En comma En equals 1. So that norm E sub n L2 equals 1. Okay, so we're that E sub n norm L sub 2 equals 1, said in different ways. Part C, the weak convergence to 0. To show that in that L2, we need to prove that for every G such that it's an element in L2, 0 to 1. Inner product, 0. For smooth G, this follows from integration by parts, or Riemann-Lebesgue lemma. So again, not all steps were explicitly shown. Integrated from 0 to 1, g of x, square root of 2, sine of n pi x dx, going to 0. For general, that g is an element L2. Approximate g by a smooth function, g sub k in L2. Then, taking the absolute value of that inner product, okay, that's less than or equal to the absolute value of the inner product of now E sub n, but now instead of g, g minus g sub k, plus the inner product of E sub n, g sub k. Okay. Part D, show that E sub n does not converge strongly to 0. I'm sorry, and extending it. My apologies. C extends here to here. My apologies. Now, going back to C, by Cauchy-Schwarz, this inner product E sub n g minus g sub k, that absolute value of it is less than or equal to a norm here of that E sub n 2, and then norm g minus gk 2, and that equals this norm of g minus g sub k 2 there. So, and now if we choose a k so large that this is small for that, okay. Building on that, then we let n, okay, approach infinity. So the inner product here, E sub n g, inner product of that, of E sub n and g, that's approaching 0, and E sub n we get. Okay, and building on that for letter D, show that E sub n does not converge strongly to 0, so we don't have strong convergence. Not strong convergence. Strong convergence to 0 would require that norm, okay, that E sub n minus 0 to approach 0, but that norm E sub n 2 equals 1 for every n, okay, or that E sub n norm 2 equals 1 for every n. Therefore, E sub n does not converge strongly to 0. And part E, explain the significance of weak convergence for existence proofs of PDE solutions. Okay, so PDE significance, weak convergence is crucial in PDE theory because bounded sequences at Hilbert spaces often have weakly convergent subsequences. This allows one to construct weak solutions even when strong convergence is unavailable. Okay, so that's number 5. Now moving along to number 6. Okay, number 6. Let H be a Hilbert space, and let that the following with M and H be a closed subspace. Sorry. So state the projection theorem. Prove the existence of a unique decomposition here. Show the following. This norm of x squared equals m squared plus n squared norm m squared plus norm n squared. Discuss how orthogonal projection is used in least squares finite element methods. Okay, so Hilbert space geometry, using the projection theorem for every x that's an element h, there exists a unique m, lowercase m, element of capital M, such that we get the following. And moreover, here, that x minus m is an element in M perp. An element M is called the orthogonal projection of x onto M. For the unique decomposition here, by the projection theorem, there exists a lowercase m such that in an element in M such that you get that norm x minus m, and you get that INF y, element m of the norm x minus y. We're going to let n equals x minus m, and then n is an element in M perp. Hence, x equals m plus n. Okay, again, m is element capital M, and n is element in M perp. Now, also, x equals m. So 1 plus x, x equals m sub 1 plus n sub 1. With m sub 1, an element capital M, and n sub 1, element of M perp. Then m plus n equals m sub 1 plus n sub 1. M plus n equals m sub 1 plus n sub 1. So m minus m sub 1 equals n sub 1 minus n. The left side belongs to M perp. Therefore, this vector belongs to that intersection, and the equals 0. Hence, m equals m, n equals n, so the decomposition is unique. For part C, the Pythagorean identity, since m is perpendicular to n, we have this, that norm x squared equals the norm m plus n squared there, expanding that norm m plus n squared equals that inner product m plus n. So we're going to get norm m squared plus that 2 times the real part of mn plus given plus norm n squared. And because that inner product mn equals 0, we could say that norm x squared equals norm m squared plus norm n squared. And for part D, least squares, finite element interpretation, and LSFE methods. And one approximates a solution by projecting it onto a finite dimensional trial space. The Galerkin or least squares approximation is often the orthogonal projection with respect to a problem-dependent inner product. The error is orthogonal to the approximation space, giving best approximation properties. And again, I apologize if I mispronounce anything. Moving on to number 7. Okay, so let H equal the following, and we want to define the following. We want to show that T is linear, show that T is bounded, compute the norm T, show that T is self-adjoint, determine whether T is compact, discuss the physical interpretation of multiplication operators. So this is a bounded linear operator problem. So linearity for the scalars, just going to go through this rather quickly. Here's the symbols for this. For your alpha and beta, here's your T. That x equals x of the following equals that alpha x f of x plus beta x g of x. Thus, we get that T of the following equals that alpha tf plus beta tg, so T is linear. So I'm just going to skip through some of this stuff, the symbols are there. The boundedness, since we have this interval, absolute value of x, f of x is less than or equal to f of x. Okay, therefore, that norm we get here, 2 squared, that TF norm, 2 squared equals the integral from 0 to 1, absolute value of x f of x squared dx equals this inequality between the two integrals. Okay. Hence, this less than or equal to this. So t is bounded, and the norm of t is less than or equal to 1. Okay. For part C, we want to compute that norm of t. We need to show that the upper bound is sharp. Let f of f sub n of x equal square root of n, and then that chi from 1 minus 1 over n, 1 of x. Okay, then if this norm equals n here times 1 over n equals 1, and also this norm 2 squared, that equals the integral from 1 minus 1 over n to 1 as the bounds x squared n dx. Since x go to 1 on this interval as n approaches infinity, this is going to approach 1, thus that norm is greater than or equal to 1. And combining with that norm of t is less than or equal to 1, norm of t equals 1. Okay, for part D, the self-adjointness for FG elements L2, 0 to 1, that inner product TFG equals that integral from 0 to 1 x f of x g of x dx, and also the inner product f tg, inner product of f and tg, that equals this integral here from 0 to 1 f of x g bar of x dx. Therefore, that inner product TFG equals the inner product of f tg, thus t is self-adjoint. Okay, moving along to letter E and F. E wants to determine whether T is compact. Okay, so let's move along to the second page here. Let's see, so determine whether it's compact. So compactness, T is not compact. To see this, define the following: G sub n of x equals square root of 2 sine of n pi x. The sequence G sub n is orthonormal, hence bounded in L2. If T were compact, that T G sub n would have a strongly convergent subsequence, but multiplication by x does not suppress high oscillations. In fact, that T G sub n has no strongly convergent subsequence, and one could show this norm, the difference between T G sub n and T G sub m, 2 does not tend to 0 as nm approaches infinity. So we can conclude T is not compact. And for letter F, our physical interpretation, multiplication operators represent observables that act by pointwise multiplication. And in quantum mechanics, a position operator multiplies a wave function by the spatial variable. Spectrally, such operators usually have continuous spectrum. Okay, so that's all for part 2, and thank you, and part 3 will be next.